Kurinji Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Kurinji Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, now we start with exercise problems, ma. So, because of starting exercise problems, I put the problem number as first problem. Okay. Actually, we completed 6 problems from Atoms chapter, no? Right? Actually, it is 7th problem, but previous 6 problems numericals only, but example, right? It is first numerical problem from exercise. Okay. See here, from exercise, right? Okay, see here, and we will discuss one by one, right? So you please be concentrate here. First problem, see this, you know, in case of first problem, it is like fill in the blanks, right? You just concentrate here, ma. Choose the correct alternative from the clues given at the end of each statement. Choose the correct alternative from the clues given at the end of each statement, right? At the end of each statement. Right? So it is like fill in the blanks, okay? Right. But they have given options and we have to choose any one of the option, right? That is, see, first A. The size of the atom in Thomson's model is dash the atomic size in Rutherford's model. The size of the atom in Thomson's model is dash the atomic size in Rutherford's model. See, there are 3 things, that is what: much greater than, no different from, and much less than. Okay, and you have to see that, you know, the answer is here no different from. So regarding the size of the atom, it is the same. It is the same in Thomson's model when compared to the Rutherford's model. Okay, right. Next, B. In the ground state of dash, electrons are in stable equilibrium, while in dash, electrons always experience. So in the bracket they have given, you know, Thomson's model and Rutherford's model. Thomson's model, comma, Rutherford's model, right? So we can correct this statement, you know. I'll read that, you just concentrate here, ma. Which is, you know, in the ground state of Thomson's model, electrons always experience, sorry, I'll repeat once again. B. In the ground state of Thomson's model, electrons are in stable equilibrium, while in Rutherford's model, electrons always experience a net force, right? So in Thomson's model, electrons are in stable equilibrium. In Thomson's model, electrons experience stable equilibrium, while in Rutherford's model, the electrons always experience a net force. Always experience a net force. Okay, right. Next, C. A classical atom based on dash is doomed. Dash is doomed to collapse, right? So the answer is, you know, obviously Rutherford's model, right? So a classical atom based on Rutherford's model is doomed to collapse. Doomed to collapse, right? D. An atom has a nearly continuous mass distribution in dash, but has a highly non-uniform mass distribution in dash. Okay, right. I'll correct the statement, you just concentrate. An atom has a nearly continuous mass distribution in Thomson's model, but has a highly non-uniform mass distribution in Rutherford's model. Okay, right. The last one, that is what E from the question 1. Right. The positively charged part of the atom, possesses most of the mass of the atom in. So the answer is both the models. That is what right, he is mentioned here in the bracket. That is what Rutherford's model, both the models. Both the models means Thomson's model and Rutherford's model. According to this question, we can understand that both the models means Thomson's model and Rutherford model. Okay, right. So here, based on this question, we understood the difference between Thomson's model and Rutherford's model, right? So in both that is what from these 5 questions, this is like 5 fill in the blanks, we understood that the size of atom is same in Rutherford's model and Thomson model. In Thomson model, the electrons are in stable equilibrium, but Rutherford's model, the electrons always experience a net force, right? According to Rutherford's model, a classical atom is based on Rutherford's model is doomed to collapse, right? Because even the electron is revolving in Rutherford's model, it has lost energy and it has to collapse. Okay, right. And here, in case of Thomson's model, atom has nearly a continuous distribution of mass, but according to Rutherford's model, atom has a highly non-uniform mass distribution. Okay, right. Next, it is what E, right? E, that is last one. So according to that, okay, right. Anyhow, both the models are indicating that positively charged part of the atom possesses most of the mass of the atom. Okay, that is what, right. So it is all about first question. So through the first question, we learned the differences between Thomson's model and Rutherford's model regarding the size of the atom, regarding the nature of electrons, regarding the collapsing, that is the collapsing of atom, and regarding the mass distribution, right, and the positively charged part and linked to the mass of the atom. Okay, so this is all we discussed with respect to both the models, that is what Thomson's model and Rutherford's model. Okay, right. Next, see here, second question, see this. Suppose you are given a chance to repeat the alpha particle scattering experiment. Okay, with a thin sheet of solid hydrogen, in place of the gold foil, right? So what is alpha scattering experiment? We know that is what gold foil is there. We are sending alpha particles, right? So some of the particles are penetrating. Some of the particles are reflecting with different angles. That is what less than 90 and greater than 90, right? Undeviated, etc. That is what we know. What is Rutherford's alpha particle scattering experiment? And that is an important question as well as important to the subject also, right? Because it was successfully explained, right? That is what the size of the nucleus and the distribution of mass in an atom, etc. It's a successful point. Okay, right. Suppose you are given a chance to repeat, suppose you are given a chance to repeat the alpha particle scattering experiment using a thin sheet of solid hydrogen, using a thin sheet of solid hydrogen in place of the gold foil. You know, gold foil means like a that is what a thin sheet of gold. That's it. Okay, right. And in the bracket, hydrogen is a, in the bracket, hydrogen is a solid at temperatures below 14K. Below 14K, that is what temperature, no? So it is like Kelvin, 14 Kelvin. Hydrogen is a solid at temperatures below 14 Kelvin, right? What results do you expect? What results do you expect? Very good question. And he is asking, he is checking. So the question is checking the possibilities, right? The question is checking the possibilities, you know, suppose if you replace the gold foil, not only here, here he is asking to replace gold foil with hydrogen, with a solid hydrogen, okay? A thin sheet of solid hydrogen. Okay, right, no problem. Not only this, if you replace gold foil with any of the various things, that is what, like hydrogen and whatever it may be. Suppose even you take, that is what, aluminum foil, copper foil, whatever it may be, right? But this type of questions makes us to think in to think in different ways. The same experiment, you know, if you replace the that is what the materials what we used to do the experiment with different types of materials, you know, it may leads to the innovation. It may leads to the innovation sometimes. Okay, you know one thing, that is what in case of Madame Curie, right, experiment, you know, accidentally, right, accidentally, not only her and most of the situations, right. Generally, I am talking about probabilities. Okay, so when you are even I think before 3-4 classes I told you the same thing. When we are going to do something, right, accidentally some of the things happen. You know, it may help a lot to the human life and development regarding science and technology. Okay, that's why like these questions are very important. For seeing the question is simple, but it gives a lot of information. Okay, see here. You know, what is the answer? Hydrogen nuclei or protons. Hydrogen nuclei or protons are much lighter than alpha particles. Are much lighter than alpha particles. Right, full stop. So, alpha particles are not scattered by solid hydrogen. So, alpha particles are not scattered by solid hydrogen. So, as the students who understood the Rutherford alpha scattering experiment correctly and perfectly, you know, by seeing this statement, that is what hydrogen nuclei are much lighter than alpha particles, you can give the answer. No need to go for rest of the matter. So, what is the answer? You know, when the hydrogen nuclei are much lighter than the alpha particle will pass through the hydrogen nuclei. So there is no scattering, there is no deviation, right? See here. So alpha particles are not scattered by solid hydrogen. Alpha particles are not scattered by solid hydrogen. Okay, full stop. They pass through solid hydrogen almost undeflected from their paths. They pass through solid hydrogen almost undeflected from their paths. From their paths. Okay. So this is what's happening in case of hydrogen nuclei which replaced in place of gold foil. Right. So the hydrogen nuclei kept in the place of gold foil. Okay. Right. Next thing, that is what third question. See here. What is the shortest wavelength present in the Paschen series? What is the shortest wavelength present in the Paschen series of spectral lines? See here. For shortest wavelength of Paschen series, you know, the values of N1 and N2 will be like 3 and infinity. So n1 is equal to 3, n1 is equal to 3 and n2 is equal to infinity, n2 is equal to infinity. And you know this formula, that is what 1 by lambda is equal to 1 by lambda is equal to capital R into 1 by n1 square minus 1 by n2 square is the formula, right? 1 by n1 square minus 1 by n2 square is the formula, right? So here you can write it as, see, the thing you can replace with, it is what 1 by lambda s is equal to R into, in place of n1 3 is there, no, that is what 3 square, and in place of this is what n2, it will be like infinity, right? And something by 0 is equal to infinity and something by infinity is equal to 0, right? So it will be 0, mathematically it will be 0. So when 1 by lambda s is equal to R into 1 by 9, that you can write it as R by 9. So 1 by lambda s is equal to R by 9. Okay, or if you write lambda s as the subject instead of 1 by lambda s, it is 9 by R. What is the value of R? It is 1.097 into 10 to the power of 7. 1.097 into 10 to the power of 7. Okay, 9 divided by 1.097 into 10 to the power of 7, right? So do this calculation mathematically. It will be given 8.2041 8.2041 into 10 to the power of minus 7 meters. I didn't write here, but if you do this calculation, you will get it as 8.2041 into 10 to the power of minus 7 meters. But I have written the value in terms of angstrom unit, that is 8 to 04.1 angstrom unit. Okay, see here, 8 to 04.1 angstrom unit. Okay, it is n1 is equal to 3 and n2 is equal to infinity. Therefore 1 by lambda s is equal to capital R into 1 by square minus 1 by infinity is equal to R by 9, right? Otherwise you can also say that 9 by R by writing lambda s as a subject, that is equal to 9 by 1.097 into 10 to the power of 7. It is 8204.1 8204.1 angstrom units. Okay, right. Next question, it is what fourth question. See here, a difference of 2.3 electron volt, a difference of 2.3 electron volt separates two energy levels in an atom. A difference of 2.3 electron volt separates two energy levels in an atom, full stop. Okay, right. What is the frequency of radiation emitted when the atom makes a transition from the upper level to the lower level? Okay, so what I am saying, what is the frequency of radiation emitted when the atom makes a transition from the upper level to the lower level, right? So please try to understand the question, what they have given and what he is asking. Okay, right. A difference of 2.3 electron volt separates two energy levels in an atom, right? Full stop. What is the frequency of radiation? What is the frequency of radiation emitted when the atom makes a transition from the upper level to the lower level, right? So in one atom, when the electron gains energy, right, it will go from lower level to the higher level, and when the electron loses energy, when it loses energy, right, it comes from higher energy level to the lower energy level. It is the thing happens, okay. But here he is talking about the frequency. What is the frequency of radiation emitted when the atom makes a transition from upper level to the lower level? and they have given the energy difference, that is what a difference of 2.3 electron volt separates two energy levels in an atom. Two energy levels in an atom. Okay, right. And in any physics problem, first we have to write the given things. That is what E is equal to 2.3 electron volt. That is equal to 2.3 into 1.6 into 10 to the power of minus 19. 2.3 into 1.6 into 10 to the power of minus 19 joules. This is the value they have given, but we are converting into joules. 1 electron volt is equal to 1.6 into 10 to the power of minus 19 joules. If you multiply this value with this value, that is 1.6 into 10 to the power of minus 19, then you will get the answer. That is, answer means E value. E value in joules. Okay, right. Next, this formula, that is E is equal to h nu. As we know, E is equal to h nu. He is asking frequency, frequency is equal to E by h, right, mathematically, and E value already we had in joules, right, and Planck's constant is 6.6 into 10 to the power of minus 34, right. So this is also available in, that is what joule second, that's why no problem, right. It is also in joules and it is like joule second, right. So finally complete that mathematical process, then you will get it as 5.6 into 10 to the power of 14. 5.6 into 10 to the power of 14 H. I will repeat once again. 5.6 into 10 to the power of 14 H. That is the frequency. That is the frequency. Okay, right. Next problem, that is problem number 5. That is what first listen the problem, then we will go for solution. See here. The ground state energy of hydrogen atom is, the ground state energy of hydrogen atom is minus 13.6 electron volt. Minus 13.6 electron volt. Okay. After that, what are the kinetic and potential energies of the electron in its state, or okay, right, in his state, in its state, right. So what is that he is asking? What is the kinetic energy of the electron, right? The ground state of energy, the ground state energy of hydrogen atom is minus 13.6 electron volt, full stop. What are the kinetic and potential energies of the electron, So it is what here, so the ground state energy of hydrogen atom is minus 13.6 electron volt. What are the kinetic and potential energies of the electron in this state? Okay, right. Total energy already given, see here, that is minus 13.6 electron volts. And the formula, that is what formula means, how can we write kinetic energy, right, in terms of the energy, the ground state energy of the hydrogen atom, and next thing is potential energy in terms of kinetic energy. Okay, see here, because very well, that is what the sum of potential energy and kinetic energy is equal to total energy, right. See this, kinetic energy is equal to minus E, that is already it is minus 13.6 and here we are saying minus E. So minus of minus 13.6 is equal to 13.6 electron volt. Next potential energy is equal to minus 2 into Ke. Minus 2 into Ke, that is equal to minus 2 into 13.6. That is equal to minus 27.2. Minus 27.2 electron volt. Okay, right. So whatever he is asking, that is what kinetic and potential energies of the electron in this state, that is what the ground state. Okay, we calculated kinetic energy as 13.6 electron volt and potential energy as minus 27, that is what 27.2 electron volt. And if you want to cross check, you can check it as, if we add these two, again we have to get this one. That is what I told you, the sum of potential energy plus kinetic energy is equal to total energy. Okay, right. So in this class we discussed 5 problems. So from 1 to 5. In this class we started exercise problems. So from first exercise problem to fifth exercise problem, we discussed 5 problems. In the first problem, we learned the differences between Thomson's model and Rutherford's model regarding the size of atom, right? Regarding the size of atom, which is same both in case of Thomson model and Rutherford's model. And in case of Thomson's model, electrons are in stable equilibrium. According to Rutherford's model, the electrons always experience a net force. And next, a classical atom based on Rutherford's model is doomed to collapse. Okay, so you can talk about collapsing of atom according to Rutherford's model. Next, atom has a nearly continuous mass distribution in Thomson's model, but has a highly non-uniform mass distribution in Rutherford model. So this is the difference in distribution of mass in both the Thomson model and Rutherford's model. Next, if you see the last one, that is the positively charged part of the atom possesses most of the mass of the atom in both the models. In both the models, this point is same. That is what last point. Okay, right. And in the next question, second question, right, we discussed that the possibilities, if you replace that helium, if you replace that gold foil with a solid hydrogen, a sheet of solid hydrogen, what happens, that we discussed. And in third problem, we discussed about the wavelengths. Okay, in case of fashion series for the respective values, that is what the spectral lines. Okay, n1 is equal to 3 and n2 is equal to infinity. And afterwards we came to discuss fourth problem, that is there itself we found the frequency by giving the energy or by having the energy difference in energy, we calculated the frequency. Okay, next in the fifth problem we calculated the kinetic and potential energy of the electron in the ground state. Okay ma, right. Thank you. We will continue in the next class.